right, we are going into a brand new chapter, chapter 9. Chapter 9 is called Infinite Series. It is my least favorite chapter in the course. However, it does start with a kind of a nice day one topic. So this is a perfect lesson for you to sit and watch at home because I don't think it's anything too crazy and something a little bit different after the last chapter that was so visual. This one really isn't visual at all. So, chapter 9 starts with the first section is called sequences, and you should have a basic understanding of what sequences are from an algebra class or even a geometry class. The idea is a sequence is a pattern. It's basically the official definition is it's a function whose domain is a set of positive integers. All that means is when you talk about the terms in a sequence, you have term 1, you have term 2, you have term 3. We use subscripts to show that, so a sub 1, a sub 2, a sub 3. You don't have a half term, you don't have negative terms. So that's why we say the domain is the positive integers. And if you want to give a generic name to a sequence, you would say a sub n is your nth term. So basically what's happening as you continue to put bigger and bigger numbers into it. Now, sequences alone are not on the AP test, so you're not going to have questions. Really, today is more of kind of getting some basic knowledge under your belt, more than actually getting you ready for exact AP questions. So it should be a pretty quick, easy day. So when we talk about sequences and the idea that they're a list, a pattern that's going on, we separate our terms with commas. The form that we're going to use the most is called the explicit form of a sequence. An explicit form of a sequence is called that because you directly plug in the term number in for n in order to get the term that you want. So if you have a first term of a sequence and we just plug a 1 in for n, like here's an example of one where we have the explicit form is 5n plus 6, and then I just listed the first 5 terms that you get. What you get when you plug 1 in for n, plug 2 in for n, plug 3 in for n, for 4, and so on. This is called an arithmetic sequence. What you'll notice about it is all the terms have a common difference of 5. They're going up by 5 every single time. We have arithmetic sequences. We also have geometric sequences. So those might be some things that you're familiar talking about in like an algebra or geometry class. We can also have sequences that have things like squared in it, so n squared plus 3. If I asked you to list some terms, when I put a 1 in, so 1 squared plus 3 is 4, 2 squared plus 3, 2 squared is 4 plus 3 is 7, 3 squared is 9 plus 3 is 12, 4 squared is 16 plus 3 is 19, and so on and so on, and you could list that. So explicit formula is really easy to work with because it allows us to plug in any number for n and it will give that term number. So if I want to know the 500th term, all I would have to do is plug a 500 in for n, which is why it's called explicit, because it's very direct. So one of the things I want you to be comfortable with is what's called pattern recognition, or writing a formula for a sequence that you're given. To me, these are kind of interesting because it's kind of like figuring out, like a game. You're trying to figure out a pattern, something you do usually when you're younger, when you're trying to do like IQ tests, things like that. So for the first one, my terms are 2, 4, 6, 8, obviously my even numbers. If I want to write a pattern for this, that would just be 2n. I'm not going to make you write the fancy brackets and say that it's a sub n, fancy brackets. As long as you have the correct notation as far as 2n, you're good. So that's how we would write the even numbers: 2 times 1, 2 times 2, 2 times 3, and so on. On this next one, we have a different pattern happening in the numerator as we do in the denominator. In the numerator, we're increasing by 1 every time. So we're just going to have a 1n. But it doesn't start at 1. It actually starts at 2. So my numerator form is going to be n plus 1. What I do is I figure out what that common difference is, and that's going to be your coefficient of n. And then you do have to see if I have to adjust it at all. So you'll kind of see the same thing on the bottom. On the bottom, you're increasing by 4 every time, which means you know you're going to have a 4n since you're increasing by 4 every time, but you're not starting with 4. You're actually starting with 1. So you have to subtract 3 off of that first one. And that's how you get a 1. And then if you put a 2 in, 4 times 2 minus 3 is 5, and then 4 times 3 minus 3 is 9, and so on. And a lot of times you'll be asked to look at fractions because fractions are interesting in that the numerator and the denominator don't have to necessarily have the same pattern going on. The next one always has a 1 in the top, so there's nothing really to that one. It's a constant. The denominator is going up by 2 every time. So 1, 3, 5, 7, 9. Again, your odd numbers. The way you're going to write the pattern for your odd numbers, it's going to be 2n because it's going up by 2 every time. But then you're going to subtract 1. And that's going to get you starting at 1. And then your next term is 3. And then your next term is 5 and 7 and 9 and so on. Next piece, I just want to kind of show you how do you get a sequence to alternate. Alternate just means to flip back and forth between positive and negative signs. So if I want a sequence to alternate and I want my first term to be negative, the way I write that is I put -1 to the n power. Because then what's going to happen when I put in odd numbers, like a 1 or a 3, I'm going to stay negative. If I want my first term to be positive, I still have the -1, but now my power is n plus 1. So now when I put a 1 in, I end up getting a second power. So my first term actually ends up with an even power and it ends up positive. So anytime you're looking at a sequence that is going to alternate, meaning starts positive, negative, or negative, positive, that's how we indicate that. We use the -1 and then have the appropriate exponent. The next one, this one is going up by 3 every time. So this is going to be a 3n. But then it's not starting at 3, it's starting at 5. So to adjust for that, we're going to do a +2. And these are nice because you can also check and see if I put a 1 in, do I get the right first term? If I put a 2 in, do I get the right second term? Next one, what we have happening, we have alternating, and it is alternating starting positive. So we know that we're going to have a -1 to the n plus 1. The numerator of all my fractions are just going up by 1. It's a 1, 2, 3, 4. So my numerator is just an n. The denominator is going up by 2, and it's actually your odd numbers. It's going to be a 1, a 3, a 5, a 7. So the way I write my odd numbers is I do 2n minus 1. That'll get my first term to have a denominator of 1, my second term to have a denominator of 3, and then 5, and then so on. So just kind of being comfortable with pattern recognition is an important skill. Here's some tricky ones. If you want to try to do these on your own and not let me give away the answer, you can definitely pause this video. These two are ones that definitely cause some challenges. The first one, first thing you'll notice is it doesn't have that constant difference. We're going up by 3, and then we're going up by 5, and then we're going up by 7. So we do not have something that is having that like constant difference or that constant slope. This one is actually related to perfect squares. That's your clue if you want to look at it one more time. These numbers are always 2 less than the perfect square. So this one is going to be the pattern n squared minus 2. So again, if we put 1 in, 1 squared minus 2 is -1, and then 2 squared minus 2 is 4 minus 2, which is 2, and then 3 squared minus 2, and so on. The next one is a special type of sequence. This is one where you're doing, to go from the first term to the next one, you're going times 2, and then times 3, and then times 4, and then times 5. And when you're continuing to multiply by the next highest number, that is actually factorial, which you might have been able to figure out just by looking at what's below here. We're talking about understanding factorials, kind of transitioning here. Factorial means that you are taking that number and multiplying it by every single number beneath it all the way down to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. So I do want to do a quick recap of how we simplify factorials. I don't know if you ever would have seen this in a math class before, but I don't think you need to see it to really understand what I'm talking about here. We're going to be working with factorials about halfway through the chapter. This is going to show up again, which is why I want to talk about it now. When I'm simplifying factorials, so 9 factorial over 7 factorial, well, keep in mind that 9 factorial is going to be 9, 8, 7, 6, 5, 4, 3, 2, 1, and 7 factorial is going to be 7, 6, 5, 4, 3, 2, 1. So the only thing that's going to be left, you're going to have a ton of things that cancel, is you're still going to have a 9 left and you're still going to have an 8 left. So that's going to be your answer there, 9 times 8 or 72, because all of the other numbers from 7 down would cancel. Same idea with this next one. 10 factorial, the 10, the 9, the 8, and the 7 would still be part of your answer, but everything from 6 multiplied down to 1 would cancel with the 6 in the bottom. So we end up with 10 times 9 times 8 times 7 for that one. And I'm not even going to bother multiplying it together. I more care about that you understand why it simplifies. The next one, just kind of getting generic. If it's generically a number plus 1 factorial over that number factorial, well, whatever the number is, you can think of it as like 9 factorial over 8 factorial or 15 factorial over 14 factorial. The only number that's going to be left is that plus 1 number, that n plus 1 number. All of the other ones will cancel. Same idea with this last one. If you have a factorial that's 2 higher than what's below it, you're still going to have that number, and you're going to have the number right under it, and then everything else will cancel. And if that doesn't make sense, just think about what it would be if it was 6 factorial over 4 factorial. Your 4, 3, 2, 1 would cancel, but you would still have the 6 and then the times the 5. The last piece I want to go through is talking about what happens with sequences as we get bigger and bigger terms. So we call it the limit of the sequence. What's happening to the sequence as we continue to put in larger and larger term number values. So as n goes to infinity is a good way to think of it. If your terms keep getting bigger and bigger and bigger and get larger and larger, we say that it diverges because it never actually gets closer to a number. If we notice that the terms actually have a finite limit value, meaning your terms are actually getting closer and closer to a finite value, we say that it converges to that value. We're going to refer to that value as L, that like we call it like the limiting value, where L is a number. And so if we know how to take the limit of a sequence and get an answer, we will be able to tell whether or not it converges or diverges based on if it gets closer and closer to a particular number, or it just get really big, or sometimes it just bounces back and forth, and I'll show you that as well. So if you look at this first one, if I look at the limit of what's going to happen with this sequence, I'm just going to call it B sub n. Well, I can use limit guidelines here. As I go to infinity, I have the same degree on the top and the bottom. So what that means is the limit of that fraction of n over 2n plus 1 is just going to be 1 over 2. That means my terms, as I keep going, more and more terms are going to get closer and closer to a half. So we say that it converges to a half because it's getting closer and closer to that number. Next one's kind of a strange one because of this oscillating feature. So if I put a 1 in here, I have -1 to the first, which is -1. So I have 3 plus a -1 is 2. But then when I put a 2 in there, that becomes a 3 plus 1, which is 4. And then when I put a 3 in, I go back to having 3 minus 1. And you'll notice that we call this an oscillating function. And because it oscillates and never gets closer to either 2 or 4, it just bounces back and forth, we say that it diverges. It doesn't diverge because it's getting closer to infinity, it's getting bigger. It's diverging because it's never getting close to one number. It's like it can't make up its mind. The next one, when we look at the limit of this one, there's a couple ways to do it. I want to show you the fastest way. Think about which one grows faster because you're putting something that's going towards infinity. The top is going to be a power rule. It's a second power. The bottom is exponential because it's 2 to an nth power. Exponential will always grow faster. And because of that, this denominator is going to overtake the numerator. So this one is going to eventually converge to 0. Because again, the bottom is what's getting bigger. So we would say that those terms are actually going to get smaller and smaller and smaller and get close to 0. Here's a couple more. So this next one, when I put 1 in, my first term is going to be 1 minus 1, which is 0. My second term is going to end up being 1 plus 1 because it's going to be a -1 squared, which is 2, and then 0, and then 2. So like the one before, we say that this diverges because it's oscillating back and forth between two values. The next one, we could use limit guidelines. So the idea here is that it is the same degree. They're both to the 1/2 power. So since I'm going to my limit as I go to infinity, I can use the coefficients and we just get 1 over 1. So we would say that my terms here converge to 1. And then this last one, I'm also going to go back to the idea of what grows faster. You could also do L'Hopital with this one if you would like, but I think it's actually a little faster. Just kind of evaluate it. Natural log grows very slowly. It's going to be like our slowest growing function. The bottom, an n is just a power function. It's to the first power. N is going to grow relatively quickly, not as fast as an exponential, but faster than natural log. So again, since the bottom is growing faster, we're going to say that this converges to 0. And finally, the last piece is just kind of talking about what do you do with something that has an alternating or a negative. If you know that if you ignore the negative part and we know the limit of that goes to 0, then your limit of your whole thing is going to go to 0 because eventually what's going to happen if you look at something like this, if I put a 1 in, I'm going to get -1 over 1. And then when I put a 2 in, I'm going to get a +1 over 2. And then I'm going to get -1 over 3. And then I'm going to get +1 over 4. And even though it is alternating, one's positive, one's negative, you're getting closer and closer to 0. And you could tell that by, if you take the absolute value and you just look at 1 over n, 1 over n, the bottom's going to get really big as you go to infinity. The top is going to stay the same. So it is going to go to 0. So those are just some basic terminology and things you should be comfortable with sequences. Delta Math doesn't have any sequences work. So what I'm going to ask you to do now is go to the quizzes link that I sent and do the quizzes on sequences. I would like you to take it enough times that you can at least get 80% right. If you took it the first time and you only got about half of them right, I'd like you to do it again and get to at least 80% to get full credit. And that is the end of sequences.